and we are recording. And this is Durwood King with Sampson Community College, and this is a class, live Zoom class for ELC 111, Intro to Electricity. And it is the most basic electrical class that we have, but it contains a lot of vital things as you go through the class that you really need. This is the basis of every other electrical class you're going to take. This is the foundation that you're going to find out. That's for residential, industrial motor controls, commercial. It's foundational for everything. No matter which way you go in the electrical field, you know you need this one to understand electricity itself. So be patient, listen good, ask questions, stop me at any point if anything's not clear. And we got plenty of time. We're not in a rush with this. So again, we are recording. I'll be putting a link for this recording later in Moodle for folks that can't participate, or if you want to go back and watch any of it. Okay.
Will we be able to watch it as many times as we want to?
Yeah, you can. Yep. And when you watch it, go to Moodle and click the link from there if you want to get credit for watching it. Like for anybody that missed today, the only way they can get credit for watching it, because there's a grade for participating in it. There's a grade for the session. And you get the grade because you're in, and then other folks that don't, they get a grade if they go in through Moodle and hit the link and go out to see it. It's in YouTube, but you have to click the link in Moodle to get to it to get credit for it. That's the only way that we have a record of who watched it. And so but yeah, you can watch it as many times as you want to. Yeah. Okay. So I'm going to do some screen switching here. We're going to start out with a basic safety video here. It's not long, but just watch it closely. And especially if you haven't had any electrical classes at all, you know, this class is geared for you. And those of you that have had classes like Victor and McGill and Roger and Benjamin, and Louise too, you're going to find out that there are things in this class that you didn't get in motor controls that it would have been good if you'd have had it before you had motor controls. Some things are going to start to clear up once you get to chapter 2, 3, 4, and on. Once you hit chapter 2 and beyond in this book, it's going to make all your other classes make more sense. It's the underlying things that we didn't cover in those other classes that you're going to be getting now. But since we don't require prerequisite classes, like on PLC class, Benjamin, you were able to take that without taking this, so that it helps you to graduate sooner and also. Okay, so I'm going to do a switch of screen here. And where is my? Let's go back out. Back out of there. I've got a lot of screens. I've got to get where I can pull up what I need here. Bear with me just a minute here, please. I've got the video in the background. Let me just get to where I can click it. I'm having a little issue here getting it pulled up. Yeah. You don't see a video screen up there now, do you, that says electrical safety? Do you see that?
No.
No, sir.
You don't? Okay, I didn't think so. Let me see if I can get it synced in now. Now I got it. It's going to link now. Okay.
There it is.
Now, so you see it now, right?
Yes, sir.
Tell me if you hear audio also. Let's go back. Now, do you see the screen?
Yep. Yes, sir.
Mhm.
Now, tell me if you hear audio. Can you hear it?
I don't hear anything.
No,
No.
sir. I do not hear it.
You don't hear any audio.
No, sir.
Now, so let me back out one time here and go in and hit share computer sound, DVD, there, and now you should get sound now. You hear it now?
Got sound now.
Yeah.
When working around electricity in any profession, it is critical to your well-being that you think safety. Electricity is a powerful technology that brings convenience to our everyday lives in many forms, but it can also be dangerous, even deadly. Certified electricians must be able to safely and efficiently install wiring, conduits, switches, outlets, and fixtures in residential and commercial buildings. Electronic technicians are skilled at repairing DVD players, stereo amplifiers, computers, and other devices found in the home. Carpenters must be able to safely use portable generators, power saws, and electric power tools during house construction and remodeling.
Hold on.
And today's automotive electrician must know how.
I put it on pause. Can y'all hear me talking?
Yeah.
Yeah.
Yes, sir.
Nicholas Lee, yeah, he thinks he needs to install Zoom on his computer. You do have to put Zoom on your computer. Well, let me ask you this: Did any of y'all join the session that you've never installed Zoom?
No, I had to install Zoom.
I had to install Zoom to
Fine.
put the link whenever you sent me the link.
Right. It told you to install Zoom, right?
Yes, sir.
Yes.
Right. You do have to install Zoom. Yes. And I forgot to tell everybody that. I'm used to dealing with students ever since about March and April, that we did all that way back then, and I've been teaching like multiple classes.
I can't even remember if I downloaded.
Yeah, I downloaded it months ago.
O sea, sapo, güey.
Actually, let me tell him right quick. He could actually go ahead and install it and then join while we're doing this. Who am I talking with? Nicholas. Yes, you could. You got time, you could go ahead and install Zoom. The 5.1, you could go ahead and install it. Do you see an option to do it? So will it not work with Apple? Right. Well, everybody has to install Zoom, yeah. But it don't take but a minute though. You could go ahead and install it and then join and then get in, jump in when you can, you know. Right. Okay. Yeah. Okay, all right. So you can just install it later, and then what I'll put the link in Moodle later today. Yes, sir. If you need anything, let me know. Yes, sir. Thank you. I'm saving these phone numbers as they come in, because doing these sessions like this, it's just, that's kind of the nature of it. It's you get hiccups with it. Now I apologize about that. All right, so we're going to start. We're going to continue the video
To safely repair super high voltage circuits in hybrid vehicles. If you fully grasp the seriousness of working with the invisible dangers of electricity, you should be able to have an
Yes, sir.
Yeah. Yes, sir.
in any related
Yes.
study. Since almost any modern career involves using electricity and electrical devices, the information in this program should be helpful to everyone entering the workforce. Electricity is the flow of electrons through a conductor. A wire is a metal conductor usually enclosed in a plastic insulator. The metal wire conducts electricity, and the insulation protects against shorting between touching wires and other objects. A basic electric circuit consists of a power source, usually the generating station, which supplies AC electricity to homes and businesses. A load, which is any electrical device that uses electricity, such as a light bulb, electric motor, or heating element. Conductors, such as wires or metal contacts in switches, carry current between the power source and the load. The conductors carry the electricity out to the load and back to the earth, or to ground. The load change.
now. Let me clarify something right here. The white wire there is a neutral wire, and it ends up, the destination of it ends up at ground when it goes back to the breaker panel. But it's considered to be neutral, and whatever amount of current that goes through the hot wire out to the light bulb, if it may be like a half an amp, if it's a 60-watt bulb, you'll find out when we get the Ohm's law that it'll draw about a half an amp. And if you got a half an amp going through the hot wire there to the bulb, it goes through the filament, lights the filament, and that same half an amp goes back on that neutral wire. So if you check the amps in both of the wires, each one of them individually, the neutral wire, also has a half an amp flowing on it too. So it's called a neutral wire. It carries the same current as the hot wire does. It carries it back to the breaker panel. And when it gets back to the panel, whenever those of you that are taking residential class, you know that when you take the panel off, the face of the breaker panel, you have ground bar on the left and then a neutral bar on the right. And your neutrals are, all of them end up when you get back to the main panel, all of the neutrals get connected over through a tie bar to the ground bar. So neutral, when it gets to the final destination, it does go to ground, and they're referring to ground here, but it's a neutral that goes to ground. Okay, so just wanted to clarify that. And they're not showing just a regular ground wire out here because that's a plastic fixture, and there's nothing metal there to ground it to. But if you have a metallic type fixture, then the framework of it would have actually a ground wire. And by the way, they call a neutral wire is considered to be a grounded conductor, ground with an ED, grounded. And then a regular ground wire that would be a safety ground for the chassis on maybe a light fixture or a motor. The ground wire is called a grounding conductor, ground with an ING. So neutral is a grounded conductor, and then the ground wire is a grounding conductor. And those are terms that that are standard in the code book, the electric code book, and that's terminology we use. So, all right, we'll continue this.
Changes the electricity into another form of energy, such as light, heat, or movement.
Now, in the case of a light bulb, it's converting electrical energy into light. And if it's a heater element, you know, everybody has heater elements at home. You've got them in your water heater. That heater element, it converts electricity into heat. You got heater elements on your stove and your vehicle for, you know, and then for movement, you know, we got motors. You know, motors are used everywhere. So electricity is converted into motion in an electric motor. So those are the three main areas of where you're using electricity to do something useful.
The term hot wire in house wiring refers to the wire that carries current and voltage to the load. Electricians often use black or red wire to carry 120 volts AC out to the load. Here is a large industrial transformer that steps down power line voltage to lower 120-220 volts AC for residential use. 240-volt receptacles use larger terminals than 120-volt receptacles, and they are arranged so that only a high-voltage plug will fit into the receptacle. Electric shock results when current passes through the tissue of the human body. Your body tissue is primarily made of water and is therefore a good conductor of electrical current. Thousands of poor souls are killed every year because of electrocution. Do not let a live electrical circuit kill you or someone else. Double check that the circuit is shut off before contacting it with your bare hands.
Now, I'll add something to that. We use lockout devices. They make lockout devices like they can go directly on a breaker. If you see them in my webcam, you see that breaker there. They make lockout devices that can go directly on the individual breaker, that you can lock out the individual branch circuit. And so, you know, we're a little tighter on it than just simply flipping it off and then going at it. And then, and I'll show you those devices when you're up here on campus. We got a variety of lockout devices. As far as the gloves, I'm going to switch to my webcam large screen here. Now, do y'all see? You see a large screen of this glove here?
Yes.
Yes, sir.
So this is the type of gloves you're going to use here in our shop, and it's what you should be using out in the industry. And if you notice here, when I go up here, you can read that the rating on it is 1,000 volts AC, and it's been tested at 5,000 volts. So that testing happens. I send these out periodically to a lab in Goldsboro to Sharp Safety, and they test the rubber part, but this is the actual part that protects you electrically. It's actually a voltage rated rubber, okay? And then you put the leather protector on top of that. Not just any leather protector, but it needs to be one that's actually listed by Salisbury, that same company there, that's listed to go with this, that's approved for it. The leather, what it does is it doesn't give you the electrical protection. It gives you abrasion protection that you don't tear the rubber part. So the real listed part here, voltage wise, that protects you is the rubber part itself. And so you need both on. You know, you may see in a video, you may see in some places somebody using these by themselves, but it's far better to go ahead and use it as a pair like it's supposed to be done with the leather on top, and it's very cumbersome. But that's the safest way to do it. Now, when I send these off to a lab in Goldsboro to get them checked, you know, they check them with a high pot. I believe they're submerging them in water and checking them that way. But they check for pinholes all the way from the tip of the finger up to here for pinholes. or tears. Now, what you can do is the OSHA recommendation is that each time that you use them, that you do this. That you see it, you get the glove out like that, pinch it like this, and trap some air in it, and then roll that glove up real tight like a balloon. Okay. And so I've got air trapped in there like a balloon, and then you squeeze and listen. And if you hear air leaking, or if you notice that it's actually going down, you need to start looking for pinholes. And if you find one, you're not supposed to use gloves. Now, you're only checking them from where I've rolled it out to the end. That's the best we can do here. We don't have the machinery, the testing facility to do like they do at Sharp Safety. So when they test them, they test them all the way out to here, So, but anyway, that's and then these, whenever you here at the college, you'll be using what we have. That's a size 10 there. Now I have a size 10 and I have a size 8, and the 8 is in a blue. When you when you go to work for a company, they're going to issue you some of these that's going to be yours. You're not going to be sharing gloves with anybody else. And if you ever, as far as the size on them where it says 10, what they do, you get a measurement by measuring around the widest part of your hand. Like in here, you get a whole measurement all the way around your hand, like in there, and that's going to tell you what size glove that you would need to have, whether it be an 8, 10, or larger. But a 10 fits, most people find here. But if you have small hands, remind me, I'll get out that size 8 that we have that you're welcome to use here. Okay. Go back. We'll continue. And as far as clothing goes, we have guys that are at Smithfield Packing like Victor and McGill. They have ARC rated shirts, ARC flash rated shirts, pants, and everything, and then they still put on extra stuff in addition to it. Here at the school, we can't provide you ARC rated clothing, but we do have a lab coats, and this is Bulwark FR, and I'm trying to get it right for the camera here. This everything's backward from what I think here. Bulwark FR, so it's flame resistant clothing. It's treated fabric, and so it's fire resistant. And when I get these dry cleaned, I got special instructions from that company there that I gave to the dry cleaner, the Glamorama here in town. So periodically I'll take them over there and get them dry cleaned, and then they got to dry clean them with a special chemical. So you can't do it. You're not supposed to use a fabric softener with flame resistant clothing, because it takes away the treatment that's in them that makes them flame resistant. So McGill and Victor, you don't wash your own uniforms, do you?
No, the company usually does.
Right. The uniform company, they know what they're supposed to wash these in, and it's specific so that it doesn't lose the chemical treatment that's in there. So that's important not to take them home and wash them and just in just any old thing, because they can end up being not being able to do the job that they're designed to do. And then as far as that lab coat there, it'll protect you all up in here down to below your knee, for those of you that, that of course don't have the flame retardant clothing. And then for your face protection, we've got a tinted, it's an ARC rated face shield. And the green color has to do with, it's a filter that filters out super bright light that can happen when you have an ARC flash. And then there's ratings, there's ratings on these, as you can see there on the side, that it's a listed type ARC flash shield. We got one down there that has an actual hard hat built onto this, but it's pretty bulky. But if you work in certain plants, then you have to have the hard hat version on that's got a hard hat built into it. And Victor, is that what y'all use? Or you use a hard hat version of this?
Yes, sir.
Right. So it's got the hard head built in and everything. It's kind of bulky, but it's, you know, where you're at, you got overhead chain track systems, carrying hogs and stuff overhead, and you got all kind of things happening above your head that could really fall and hit you in the head. So
Yeah, hard head.
you got to have a hard hat, you know. You sure do. You really do. Insert the butterball. It's required, I think, in a lot of areas. You know, so that's another thing.
Yeah, basically, if there's anything over here, you're supposed to wear them.
Yep. Absolutely. Okay.
And I've seen some stuff fall.
Yeah. What, for instance, what have you seen fall?
Some threaded rod that was pretty old. They used to run some power there, some rubberoid. That thing fell.
Threaded rod that was being clamped to your ceiling.
Yeah.
And it fell like a spear, didn't it?
Yeah.
Man.
Yeah. And a gearbox.
A gearbox fell out there.
Yeah. Gearbox and motor, everything.
Bad. So when it fell, did it how close did it hit anybody?
Well, they were just standing there. Well, it was at startup. Victor seen it. Victor was there.
Wow. Man. Okay. Here we go. Back to this one. The gloves, do you see this guy's got on? Now, we're using real voltage rated gloves. So the only reason I'm using the video is because it has got some beneficial things in it.
Working around exposed house wiring, always assume the wires are hot or carrying current and take necessary precautions. With a 60-cycle 120-volt circuit, the amount of current passing through your body will determine the amount of injury. At approximately 1 milliamp, you will begin to feel the current. At about 10 milliamp.
Now, as far as current goes, you know, when we talked about voltage, and we talked about current, and we talked about resistance yesterday, the three basic measurements for doing electrical measurements. When you measure current, we measure current in amps. And if it's a small fraction of an amp, that's called a milliamp. And a milliamp would be 1,000th of an amp. And just to give you an idea, a 60-watt light bulb would draw half an amp, which would be 0.500 amps. 0.500. Here you're talking 0.001, which is a whole lot less than a 60-watt bulb would draw. And then a power drill that you would plug in, it could draw 3 to 4 amps, whole amps. And so that can kind of give you an idea that how small this is, that you can actually feel it when you only get 1 milliamp of current going through your body. You can feel a tingle.
Amps, the current may paralyze muscles.
And now at 10 milliamps, which is only 0.010 of an amp, you can actually have something called a muscle contraction. So if you have some leakage current getting through your body of 10 milliamps, that amount of current is actually enough to override your muscle control. Now think about it really good here. Your body is actually bioelectric on the inside. You have small electrical signals that go from your brain to your muscles that make your muscles do what they do when you want to pick something up or walk around. You got small electrical impulses that are going through from, like I say, brain to your muscles that control the muscles. Okay. Now, external electricity coming into your body from installing a light or working on a motor or whatever it may be, outside electricity that gets through your body, if it gets in the range of 10 milliamps, 0.010, at that point, it becomes stronger than the electrical signals from your brain to your muscles, and it actually overrides your brain, and it can make your muscles do that. So you could end up clenching onto a hot wire and unable to let go. And even though you want to let go, you would not be able to. It's just around 10 milliamps, and that's extremely important. While we're at that point, I'm going to throw something in here that where we're heading in this in safety is we're going to be talking about ground fault circuit interrupters, GFCIs. Can y'all see that receptacle I got in the webcam there?
Yes,
Yes.
sir.
Yes,
Yes,
sir.
sir.
Do you recognize, where have you seen one of those out before?
Bathrooms.
Right, bathrooms,
House.
Kitchen.
kitchen, right. Now, what these things here do, I'm going to tell you in a nutshell what they do, the way they work. Now, some people think that they work like a circuit breaker, but they're different. It's a whole different thing. First of all, a circuit breaker, what it does, this says 20 on it, so it's a 20 amp breaker. And what it does is when the amps that's going through a wire out to a receptacle, for instance, if you draw more than 20 amps on the receptacle, then this thing here is going to trip, okay, if you get above 20 amps. If it's a 15 amp breaker, you get above 15, that's going to trip. That's called an overcurrent device. It's an overcurrent protection device. If you go above that, it's going to trip. A GFCI is a whole different thing. What it does is it detects if you have missing current or leakage current in that. If I plug in, if you're at home and you got a hair dryer and you plug a hair dryer into this in your bathroom, now the little narrow slot there, the narrow slot on this side is actually the hot wire. As y'all saw in your lab that you were wiring up Tuesday, the narrow slot is hot. Now, if you plug a hair dryer into this, then your hair dryer draws so many amps out of that hot there out to through the heater element in your hair dryer, and then it comes back on the neutral. And then, so if the hair dryer happens to be drawing, say, 3 amps, okay, just a ballpark. If it drew 3 amps out of that hot wire, and it went through the heater element in the hair dryer, and it came back on that neutral, then the electronic sensing circuitry inside of that little GFCI there, it's got electronics in there, and what it does is it compares. It compares. Here you've got a black wire on this side of the receptacle. That's your hot, and then there goes your white neutral right there. So within a GFCI, it has electronics in there that compares the amps that's flowing on the black wire, and it says whatever amps that went out to the hair dryer should be coming back on that neutral wire. It should be identical. And if you have 3 amps going out on that black wire going to that hair dryer, and you got 2.5 amps coming back on that white wire, you got a 0.5 amp that's missing, that's unaccounted for. And so that's called a ground fault. So if I got 3 amps going to the hair dryer, I got 2.5 amps coming back on the neutral wire. What happened to the 0.5 amp? We don't know, right? We don't know. So here's what we assume. We assume that it went to ground. We assumed that it went to ground. It had to go somewhere, and we assume it went to ground. And then when that happens, it's called a ground fault. Because look, on a ground wire, you see that ground wire, that bare ground wire there, there's not supposed to be any current on that ground wire whatsoever, none. Now the ground wire, on whatever you plug into this, the ground wire goes to the metal parts of whatever appliance or whatever you're plugging in to the receptacle. So it's a safety ground, a chassis ground for whatever plugs into the receptacle. On the ground wire, you're never supposed to have current on the ground wire. It's just there as a safety to keep that chassis of that appliance or that device, to keep it at ground potential, to keep it at 0 volts. So the framework of whatever you plug into that receptacle is actually going to be forced down to be at ground potential as far as voltage. It's not going to be floating. The frame or chassis of your device is going to be at ground potential. So when you touch it, it's going to be the same thing. It's going to be harmless. Okay. So when you have missing current in a hair dryer or in a hand drill or whatever it is, missing current, here's what can happen. Okay. The missing current could possibly end up getting in your body and going to ground through you. And here's what happens. The ground fault circuit interrupter, what it does is if it sees a difference in the current on the amps, if it sees a difference of around between 4 and 6 milliamps, if it sees somewhere around 4 to 6 milliamps of current difference between these, to where you're missing around 4 to 6 milliamps coming back, what happens, it trips on the inside. Then it trips like a breaker does. It has a trip mechanism that's built into this thing, this internal. So it does have a breaker. It is a breaker, but it trips based on an imbalance of current between the hot wire and the neutral wire if they're not the same. If it's missing current coming back unaccounted for, and if it's in the range of 4 to 6 milliamps or greater, then this trips. And the reason why it trips around 4 to 6 milliamps, now listen close here. The reason why it does it, the trip point on this receptacle is around 4 to 6 milliamps is because of this number that we see on this screen. What amount of current do you see on the screen right there? What do y'all see on the screen right there? What does it say? How much current can
10
actually
milliamps.
10 milliamps can paralyze, can actually cause you to have a muscle contraction and paralyze your muscles. 10 milliamps can do that. So look, this ground fault receptacle, it trips around somewhere in the range of 4 to 6 milliamps is when it trips. So it trips before you hit 10 milliamps going through your body. That's the reason why this here is designed with a particular trip level below 10 milliamps. These are designed several milliamps below 10 milliamps. Now you could have 2 or 3 milliamps of leakage current and this would not trip. But if you got around between 4 and 6, somewhere in that range, that's where that GFCI is going to trip. And they call it GFCI because who knows what the 4 letters mean of GFCI?
Ground fault circuit interrupter.
That's right. Ground fault. Now we talked about that. And when we say ground fault, then we say that some of the current in that circuit did not return through neutral back to ground. It was not a complete circuit and there was some missing stuff, missing amps, coming back that should have been on that neutral. Now, literally what happens inside the GFCI is this, is it literally takes, let me show you real quick what it does. You see that clamp right there? This is a clamp device that can plug into a regular digital multimeter, and it can let a digital multimeter read high amps by putting a wire inside that coil. And if you put a conductor inside that coil there, then whatever's inside there, it's going to read the amps. When you plug that into a digital multimeter, it'll let a meter read it that doesn't have a clamp in there. So it's a current clamp that senses current and senses amps. Now, actually inside of the GFCI, what you have here is a very small version of this. There literally is a current pickup coil inside the GFCI receptacle. Here's what it does, literally. I mean, if you read the paperwork on these things, next time you get one or when you come to school, we can show you the paperwork on one. They tell you that inside of this thing, there's a small current pickup coil. Here's what it does. They take the hot wire and the neutral wire, both of those, and they run them through a current pickup coil like this. Both of them. Now, normally, when you're reading amps, you don't read but one wire. When you start using the meter here to check volts and amps and everything in the shop on your labs, when you check amps, here's what you're going to do. You're going to run one wire through that current pickup, that current coil there, and the meter's going to tell you how many amps is on that one wire. Now, here's what happens when you put 2 wires through a current pickup. If I put 2 wires through the current pickup coil there, here's what the meter's going to read. it's going to read the difference between the two. Now, listen real good here. You got current flowing in one direction out, in one direction here out to a load, and then it comes back in this direction. So they're flowing in opposite directions. And here's what happens. The magnetic fields in these two, when you get them together and you put them in one coil that way, if they're identical in amps, the magnetic fields cancel out. And that current coil actually, when you plug it into a meter, the meter says 0. If you put two conductors in a current clamp and the current's going one way in one and coming back the other way on the other one, the magnetic fields will cancel out in there, and then the meter says you have 0, which means you got 0 difference between them. Now, in the case of having some leakage current, if I had 3 amps going out of the hot wire to a hair dryer and 2.5 coming back, here's what the GFCI sees. Here's what it sees. Inside, when you run the two wires inside the GFCI like that, it will say the current, it will say 3 amps minus 2.5 amps, and it sees a difference of how much. What's the difference between 3 amps and 2.5 amps?
Half an amp.
A half an amp. So look, that current coil that's inside of that GFCI, it's a small one in there, but that current coil picks up that you got a half an amp of difference between the current, between the amps in those two wires. And a half an amp is enough, more than enough to trip that. Has everybody got that?
Yep.
Yes, sir.
So this thing here is not, it's not an overcurrent device like a breaker is. A breaker works when you get above 15 or 20 amps, and below that, that breaker is not going to save your life. It ain't going to save you. The breaker, what it's designed to do is to keep you from melting down wires and melting down devices. So the breaker is only for circuit protection, to protect wires from burning up. In other words, if I've got a number 14 wire here, and I got a 15 amp breaker, and I have a short circuit in this receptacle or something plugged into it, then what's going to happen is you're going to draw more than 15 amps, right? So then the breaker is going to trip. If the breaker was rated too high, for instance, like what I got here, I've got a number 14 wire here that's rated for 15 amps. I got a 20 amp breaker here. So this is not a good match. If something goes wrong in this circuit right here, and I draw more than 15 amps, then what can happen is this ain't going to trip until you get to 20 amps. So you got about a 5 amp window in there that you could actually overheat that wire and have a fire hazard. So you always want to match up, and as we get into this further in this class and in residential, you're going to learn how to go to a wire chart and pick the right size wire for the right circuit and have your devices matched up with the device and the wire size and the breaker, everything matching up good so that you don't have a fire hazard, and in comparison, the GFCI, it trips based on ground fault current or leakage current in a very small range, around 4 to 6 milliamps, where this is for overcurrent. So for your circuits like this in your bathroom and your sink and outdoors and all your garage, you need this if you're near water, like within 6 feet of a water source. And you need this ahead of it in the breaker panel. So the breaker itself is going to protect the wiring. It's going to protect the wiring and the devices that are there. It's there to protect the equipment, okay? And then you have out there where you are, you've got the GFCI receptacle, and that is for you. That's to protect, to keep you alive. So does that make sense?
Yes.
Yep.
So you need both. Now, you can buy breakers that have a little pigtail neutral coming out of them. It's a special breaker that you wire up in residential wiring that you guys are going to be doing, you know, in a couple of weeks. You're going to be doing ground fault wiring and all, and arc fault breakers. But they do make breakers that have the GFCI built into them and overcurrent, so you can buy them combination that way. And they also make arc fault breakers that we're going to get into. We get into that in residential, but it's the new thing out is arc fault breakers, and what they do is if it's a special arc fault breaker, it can sense if you have wires maybe like in that cable right there. If you had, for instance, somebody that stapled that cable on a stud in a house, if they stapled a little bit too hard with a hammer, and then it penetrated into there, and over time, if you had this black and white wire that actually got shorted together a little bit in the cable and started arcing like a spark plug does, you started getting a little bit of sizzle in there. You can have small amounts of arcing in there, and it'd be way below the rating of a breaker. So the arcing can happen. It can happen where a staple is, or it can happen where someone, whenever they were making their connections in a box, they didn't get everything covered up good. Maybe they nicked the wire in here whenever they cut the jacket off. You know, when you cut the sheath off, if you actually nick it in here and don't see it, you could end up having a nick in a hot wire touching a ground wire right up in here possibly. So anywhere it's possible to have arcing going on in a lot of places. And the point is, the arcing can be a small amount of current, okay, to where this breaker won't trip. But the new arc fault breakers, they will detect the characteristics of arcing. So the breakers that are arc fault, we got them in the shop in there that you'll be doing in residential at night, they have electronics built into them that looks for the characteristics of an arcing pattern electrical. What does it look like? What they call the signature of arcing. Like if you were looking at an oscilloscope, it'll have a signature to it. What does it look like on the screen? And the arc fault breakers have electronics in them that actually looks for that kind of signature. And they can pick up what they call parallel arcing. Parallel arcing is when you got two parallel wires like this that travel together, a hot and a neutral, that are in parallel like that. And that if they arc together somehow through a failure of insulation, that's called parallel arcing. And the arc fault breaker will trip when it sees that. Then you have something called series arcing. Now let's say if I had a receptacle like this, and I had I didn't tighten up that hot screw right there very good. And over time it kind of worked loose. And then over time, as I had something plugged into it and was drawing current, that screw connection right there, because it was loose, it begins to arc a little bit to where it's not connected nice and tight. So it starts to arc. Well, this is considered a series arc, to where you have a hot wire here going to the receptacle. You got a device plugged in like a drill or hair dryer, and that hot wire it actually makes and breaks. So it's like doing this. It's like taking a hot wire and breaking and making and breaking and making. So that's called a series arc. So if you have one wire that's making and breaking repeatedly like that, and you have arcing going on, it's called series arcing. So an arc fault breaker that you can see in residential, or we can show you in this class, we can show you what they look like. They actually will trip if they sense any kind of arcing whatsoever. If you have a hot wire arcing the ground, it's going to pick it up and trip. And they invented those breakers like that some years ago because there was house fires and people dying over loose connections on receptacles and different kinds of issues with arcing going on that a regular breaker could not detect. Again, that breaker only works if you go above the rating on it. Arcing can be way less than 15 amps. It can be, a small amount, way less than an amp it can be arcing in there. But you can have a fire to develop with an arcing that goes on below the rating of the breaker. So that's why they came up with this special breakers that are required in all your houses now. So if you have a new installation now, a new house wired, then all of your living quarters has to have arc fault breakers in the panel. And every area in the house has to have it except for the bathroom. And the bathroom has to have that right there. So in the kitchen, you got to have that, and you've also got to have an arc fault breaker ahead of it. So in the kitchen, you got to have arc fault and ground fault protection. And you can buy a breaker that does all of that together. You can get an arc fault, GFCI breaker, all that all rolled up in one. You're just gonna pay more for it. I prefer to have these at the location of where you're going to use them. So if they trip, then it's visible that it's tripped. You're going to see it, and you can actually reset it right there instead of having to go to a breaker panel to reset something. So it's better to have the GFCI receptacles and then do if you're doing arc fault breaker like for kitchen, then to do the arc fault breaker ahead of a GFCI receptacle. So we get into that stuff in residential and where you physically wire all of those. Okay, that's a lot said, already with what we're doing here. Any questions so far?
Not me.
Oh, sir.
No,
No,
sir.
I'm good.
Okay. And they do make a pigtail version of this that's that's about a foot or two long, that's got a male plug on one end, a GFCI box, and then it's got a female plug after it that you can portable carry around. You guys have those, don't you, Victor and McGill, at work?
Yes, sir.
It's a portable ground fault pigtail. It'll work to where you can plug that into any kind of receptacle and you can have ground fault protection. And that's something that y'all definitely need to be using out there because you got a lot of water out there. A lot of places you go is wet. And if you're using power plug-in tools, you need to have that ground fault protection there because you can get electrocuted. You can actually die from using a power tool. If you get wet in certain conditions, you could actually die from it.
I got lit up yesterday.
You got lit up?
Yeah, it's just 120.
So what happened?
It was a fan, but I guess a jack driver ran over the cord, and they didn't tell me. They said the fan wasn't working. I just went under, picked the cord up, and got me.
You picked up the cord right at the place where he ran over, huh?
Nah, they didn't tell me, and they didn't tell me all that. I just picked up the cord, and lit me.
But where you picked it up at, it just happened to be where they damaged it.
Yes, sir.
Man.
Got me wide awake.
And listen, everybody listen to this. Don't think this stuff is boring because it's not. We got to think before we get into doing this stuff. I mean, I had y'all doing something the other day, but everything was locked out. There was zero risk on it. But when you start to test everything, you're gonna have the gloves on and all. We really got to put there's a whole lot of thinking and we got to get a lot of things understood here up front that can happen. Now, let's think about what happened to Victor there. Somebody ran over a cord for a fan. Now, do y'all wonder why did the breaker not trip? Has anybody thought about that? Why didn't the breaker trip? Now, here's kind of what evidently happened. The jacket on that cord got damaged, but you didn't have a hot wire shorted to neutral, and you didn't have a hot wire shorted to ground. You didn't have either one of those, huh?
It was just the hot wire, the one that was cut.
Now, so it was only the hot wire that was cut, exposed, and you didn't have a short circuit condition that could trip a breaker. But yet you had an exposed conductor that got you, and then when it hit you, went through your body and it went to ground. And that's what we're talking about, everybody. We're saying that electricity is going to try to go to ground. You know, lightning, when you see lightning is looking for ground, and it'll hit a tree, it'll hit a light pole, man, it's looking for ground. Electricity wants to find ground, you know. It's looking for a lower potential to get to Earth. It's looking how to get to Earth. And it did. So what, describe how you felt, Victor. How bad was
it? It wasn't that, I didn't feel it that bad. I mean, I got shocked before with 277. That hurt enough.
Yeah.
But yeah, I guess it wasn't that bad. 277, that's painful.
Yeah. When you got shot with 277, what did it make you feel like? Can you describe that?
It's just like a big hit, you know, like as soon as it hit me, my hand just like went numb.
Something hit you? Did it feel like a hammer hit it, or what?
Like something bit me, you know, like it hurted real bad, and then
Something
my
bit
hand just went, yeah, if my hand just went numb.
Mm-hmm. Yeah. Right. That's why we need these. I mean, so we need. But honestly, now, if I was walking around and all I was going to do is pick up a cord off the floor, a fan cord, now, you know, you wouldn't think that you would need to put these on, would you? Because you shouldn't need that just to pick up a cord off the floor, right? But that was one of them times where, you know, that's rare. That's for something like that to happen, but it happens sometimes, and I'm glad you're okay. So.
But I'm extra careful when it comes to high voltage 480 and all that. I double check everything before I touch anything. I know breakers can fail, and a lot of things can go wrong.
Right. And let me tell you something that you really need to be doing. That OSHA recommends, and I want you to watch. This is simple, but it can save your life here. So I'm gonna go to my webcam, a large view here. So I'm gonna hit stop share here real quick. Now, do you see my webcam real big now?
Yes, sir.
OSHA gives a three-step procedure that you should be using anytime that you're going to lock out something before you're going to work on it. Now I'm going to show you. It's very simple, but this is what you should be doing. And some people will chuckle and say, "Well, hey, I don't need to do all that," but we really do. Now watch. Now here we've got a motor control center right here. Let me back it up. So y'all see here that we have a unit here that's got a circuit breaker in it. It's got a motor starter. It's got some lights and all. This is a main disconnect. It would be for one motor control center. So let's say that I've got to work on the motor itself, the motor that gets connected to this, where the wires go out of the motor starter and go to a motor. And I want to disconnect. I'm going to work on the motor, okay? So I come over here and I cut that off. Now, the next step you're supposed to do is this. You're going to take a lockout device like this. You're going to put around the switch like that. Then you're going to take your lock. You put your lock around that. You got the key. You pull the key out. That key's yours. Nobody else gets it. That tag is going to have your name on there, and nobody's got a key but you. Then you want to test voltage and see is just dead. Okay. Now, before you do that, before you actually test that to see is it dead, then you want to do this. They tell you to go to a power source that you know is hot to verify that the meter is working properly before you go check that dead circuit. So we're going to go here, and on the meter, where do I go if I'm going to check, if I'm going to check voltage here, what do I put the meter on?
On the
You put your meter on your volts.
Right, on volts. And here for volts, it says it'll pick up AC or DC automatic selection. Do y'all see that?
Yeah.
So it detects either one. Right now it's saying AC, but if you come in contact with DC, like on a forklift or a car battery, it'll switch and it'll tell you that it's DC up there. It knows. Okay. So let's go here. And we're going to check a receptacle that we know is hot, and we're going to make sure the meter's okay, because just because the meter was good last time we used it don't mean it's good today, right? It may not be. So we're going to go here to our hot terminal and to our neutral, and we're going to measure that. And then what does the meter say?
120 volts. Well, 121.
121 AC. So now you take your meter and then you go out to where you've locked out that panel. The circuit breaker that's in here, the power comes in to the back where it plugs into a wall structure. These clips back here, this whole box plugs into a set of hot bus bars in a motor control center. And you've got here, you got like 3 hot wires and you got a ground up in here. So if I from the inside there, if I measure from each of those 3 hot legs at the bottom of that breaker and go to ground, then that should be indication that it is dead. Okay. So if I go, I got to get the meter position right. If I go and I check one of the hot wires in there, I go inside where the breaker is, and I'm checking one of the hot wires leaving the breaker. There's actually 3 of them in there. And I go there and I find me a ground point in this panel, a place I can get in contact with ground. And I'm finding me a ground screw right in here. So the meter says 0, right? So that first leg on the breaker is dead. Then I go to the next leg on the breaker in there, right? And I go to ground and it says 0. And then I move to the third leg on the breaker inside there because it's 3-phase power. I go into there, and Louise, this could be 243 phase, it could be 483 phase. I know they're telling you they want you to learn about 3-phase. Now, 3-phase, you're going to work with that in motor controls in January. Okay?
Okay.
We don't deal with 3-phase.
Right.
We don't deal with 3-phase in this class. You're going to stick with single phase. But starting in January, from January to May, you will deal with 3-phase pretty regularly. But that third leg, we're going to check there, and we're going to go to ground. And we also see 0, right? So you're good to go. Now, that said it was 0. Now, that's the second step that OSHA says you do. You check it on a known hot circuit, and then you check the one that you're going to test. Now we know that the main power feeds in from the back bus bars here, from here where it plugs into a wall structure through the breaker panel, so to the breaker. So if the breaker's dead, we know the rest of it's dead. Everything else is downstream, you know, here in this motor control, okay? So we saw that was dead, and then our third step is this. Now it may seem redundant, but just bear with me here. OSHA says you go back real briefly, go right back to the same hot circuit that you checked a while ago, and you verify that the meter is still operating properly. And you see that it is, right?
Yep.
Now,
Yes, sir.
That's a 1, 2, 3 step. You checked it with a known hot circuit. Then you went and checked your breaker on that motor control bucket there, and you saw it was all dead. All legs are dead. Then you came back and checked this one more time. And what that proves is, beyond a shadow of a doubt, that the meter is fine.
Hey, Mr. Durwood, I got a question.
Uh-huh.
Okay, for your resistance and the meter, you're supposed to get, like, if you do resistance between the leads of the meter, you're supposed to get somewhere between 0 and 1, right? Between the meter that shows that it's accurate.
On resistance.
Yeah.
On ohms. Okay. Yeah. Right. That's correct. Let's do that. Let's get it where you can see that. Now, what we're talking about here is when you go to ohms, you go to resistance there. When you have the leads apart, it says OL for over limit. And over limit means this. It means that on resistance, you have a maximum of what? 1K ohms. What does K mean?
Kilo
Kilo ohms.
Kilo ohms.
So this meter it won't go any higher than 1 kilo ohm. So when you're above a kilo ohm, it says OL. Now it doesn't know really, do you have, 2 kilo ohms or 1 mega ohm? It doesn't know. It just knows that you're above a kilo ohm. Now, the way you can actually check the resistance of your test wires, of your test leads, let's move the camera up.
Because sometimes that can get you. I mean, if it's not right.
Now look, here, this meter has got, the meter has test leads that are built into it, and so the test leads themselves have resistance to the leads themselves. So if you want to see what the resistance is of the leads, then you just put these two together. And let's go back down here. Set that down. You just touch these together. And see, that says 3, 2. Now here, you've got quick connects that can be an issue. So if you take the quick connect apart, I don't particularly like these. But you do that and you want to reseat it and take that out and reseat that again and try it again. So you have 2 ohms of resistance in these test leads. It's better if it's actually below 1, but there is a little bit of resistance in there. And what that can do is it can make a very teeny little, it can throw accuracy off a small amount, not a lot, but a little amount. When you're reading around 120 volt and up, it's not going to make much of a difference. It's not going to hardly affect you. If you're doing low voltage readings, low voltage DC readings, and it may affect it a little bit more, but it's still not going to be a major issue with 2 ohms. But if you got 5, 6, 7 ohms, it's a concern. You really need to be replacing your test leads. But here,
That's what I'll do every morning. I'll check mine.
right. Basically, what you would do, here's what you want to do, is if you're checking the resistance of a heater element or something to work that's got ohms to it, and you want to know is the ohm reading of the heater element okay or not. The first thing you do is you put these together and whatever number that is, you would subtract that from the reading you get on the heater element. So if you have a 2 right here, just in the travel of the test leads, 2 ohms of resistance, and then you go across the heater element and you get, say, 16 ohms. You would say 16 minus 2, and it would give you a real resistance of 14 ohms for the heater element. Okay? Does that make sense?
Yes, sir.
I've got a meter.
Yes,
I don't have it in here, but I've got one at home that's got a button on it called REL for relative. And when you put the leads together like that and you hit the REL, the relative button, it actually zeroes the screen. It does it like a weigh scale if you're going to calibrate a set of weigh scales, you know. That basically, if you're calibrating the scales and there's nothing on them and it says 2 pounds, and you hit the tare button or the clear button on the weigh scales, it'll zero it. A relative button on more expensive meters, it just says REL for relative. And what it'll do is whenever you do whatever you're going to do and you hit relative, it will actually null out that reading and make it be 0 from that point, you know. So, but you can mentally, you can just do that. Mentally, you can do that and you'll be fine, you know. But if you got test leads that are, you know, that are 5, 6 ohms, something like that, I'd be replacing them, you know. These, you got to take the meter apart and put them in there. I prefer, let me show you a set that's actually better than that, and you'll see the difference. So these are way more expensive leads right here. They got quick connects on them, but they got way less resistance in them. It's more of a more expensive meter. And you get into using this a little more later on, like for motor controls. So we're going to go this meter here. You know, it's got more features on it. You know, you go to ohms there like that, and
You can even do installation tests on that one.
you can do, yeah, you can do installation test on motor leads, all that stuff. Yeah, right. But here you put these together, 0.6. You see that? 0.3 ohms. You know. That's a lot better, you know. So even those these have quick connects on them, it's just a much higher quality set of leads, you know. .3, so it's only a third of an ohm, the resistance of the quick connects and the leads themselves. But this meter doesn't have a relative on there, but if it has an REL button, you hit that while you got the leads again, and it'll null that out, you know. So, but anyway, they're all good questions. What issues have you had with test leads, Victor? That you said it was throwing things off?
Well, not me, but a coworker. One time he let me borrow his meter, and I was actually ohming something out, and I was like, something ain't right with your meter. And I put it, he was like over 20 or 30.
Okay, so it was time to replace those leads, you know.
Yeah.
And what you can do as a diagnostic would be this. Now, let's say this meter here that has a detachable leads on there. If you put them together and it said, you put them together and if it said, say 20 ohms, it says 0.3 right now. Let's go here. Let's say if it said 20 ohms, then what you can do is look, you pull out the black lead, and you can take the red one, and if you can make contact down in there, let the red lead go in and out and see, is it the red lead doing the problem? And that red lead's fine at 0.2 ohms. You see that?
Yep.
But you got to have leads that'll actually have, like these leads are, they've got shrouds that pull off like that, where you get safety protections there. Then they pull off, and they've actually got a banana plug right there to plug into a regular meter plug. So you can actually do it that way and actually just test that one wire.
Yeah, his was a basic meter. It was a T5 600, I think.
Right.
Yeah.
So if it's like that and they're actually built in, you got to take the meter apart to get the leads out of it, because they're, you can't unplug them. But you could still do a loop test for each wire once you get the meter apart, and check and see which lead is it, or is it now my point here is if you do this and it's not good, and it isn't good, and you do the same thing with the black test lead, and they both read bad, then you might want to take you a piece of solid ground wire, a piece of bare wire like this. Take you a piece of bare wire like that and go jack to jack and see, is it the meter, Or try another set of test leads. Get a different set of test leads from somebody's meter and see, does it, is it the leads or is it the meter? Because I mean, I've had to send a meter off and get a meter worked on before, So don't assume it's the leads, because it actually may be the meter itself getting something wrong on the inside. Could be. That's a real possibility. Especially where y'all are using meters. Your environment is pretty tough. You got a tough environment there. A lot of things meters can get beat around and everything a lot. So but anyway, so we've only got a few minutes left. Let's go ahead and let any other comments at this point? If not, let's let the video finish. Now, out in Moodle, let me just show you real quick before I forget. Let me show you in Moodle the assignments that I have out there you can be working on. Just bear with me here a minute. Now, do y'all see my Moodle page now?
Yes, sir.
You see the welcome mat?
Yes.
Now watch closely here. When you go down in the welcome mat, now this is where the link was where you got in this session here. Now below it is where I'm going to put the recording at later on. Now, here you want to go in there and read. There's a electrical safety lab. It's actually a written thing that you read on electrical safety. Click and go in there and you read this and answer some questions that are in here that go together with that safety handout lab there, okay? And then the textbook, in the textbook chapter 1, in the textbook chapter 1, this is chapter 1 out of your book if you don't have your book yet. So let me just show you real quick here. This in the webcam, do y'all see that? That's your textbook.
Yeah, I got one of those.
Right. If you don't have that book, chapter 1, I copied it, and look on the screen there. I scanned it right there. So that's chapter 1. You can download that and read it. And we're going to go over that. Next Thursday we're going to go over book stuff and Tuesday, we're going to spend doing shopping. Each Thursday is going to be doing like what we're doing here. But you can go ahead and read that chapter, and you can answer those few questions in there. It's very, very basic. And then, hold on, I'm sorry. This is a safety chapter that's not in the book. You need to download the safety chapter. That's a safety chapter. You need to read this book does not have a chapter in the beginning on safety, but you need one, so I've stuck one in here. So you download that because it's not included with the book. Download a safety chapter, read that, answer some questions in there. There's a worksheet on that whole chapter there. And then the textbook chapter right here. There's chapter 1. I scanned the whole chapter. There goes your worksheet for that. So you got 3 things in there that you can, and all of them are basic. It's all basic stuff. But we have to cover safety aspects first before we go very far with this, you know. So now go back to these are do y'all see? Do you still see my Moodle page here?
Yes, sir.
These are handouts I've been showing you. You can go in there and download these. In other words, the definition for voltage and current, I think I gave you one of them. Ohm's law, you can download the Ohm's law formula sheet. If you click it, then it shows you Ohm's law. Do you see that? Do y'all see that pop up there?
Yep.
You do? With the triangle, you see that triangle there with EIR in it?
I don't.
Don't.
You don't see a
No.
triangle there?
No.
You don't? Okay, hold on. How about now?
I see it now.
You see it now. So look, the triangle has got Ohm's law in it. We're going to be looking at how does Ohm's law work, and the triangle gives a basic form of Ohm's law to where all of the formulas are in that pie. You see that pie chart there? You see the big pie chart?
Yes.
You do it? Did you say you did?
Yeah.
I still
Okay.
see it.
So that's something you can download and save on your computer. You can download and save it on your phone too. There's another triangle up here that involves power, voltage, and amps. So that's a power triangle there that's got watts, volts, and amps. And both that triangle and that one, all of them are derived out of that pie chart. Everybody's going to be using a lot of this stuff in here coming up really soon. When you hit chapter 2, we start a lot of calculations on circuits, calculating volts, amps, and ohms on all kinds of circuits with heater elements, light bulbs, and motors. Okay, it's going to get pretty deep pretty quick, kind of like stepping off in a pond to where it's ankle deep, and all of a sudden, wham, bam, you're knee deep before you know it. That's what's getting ready to happen in chapter 2. So you know, get your waders on because it's going to get deeper pretty soon here. Okay, and then you go back to the other. You see my Moodle page again?
Yeah.
The metric
Yes.
prefixes that we talked about in the metric system, if I click that, and then I do a screen share, there goes the metric prefixes that I've been talking about. That says, you see where I'm pointing at milli, like milliamp. You see the milli with the thousands right there, the lowercase m. You see that?
Yes.
Here, we use the short scale metric system in the United States. Most of the world uses the short scale labels for metric prefixes. Some areas of Europe use long scale, like they might call, instead of calling a billion, they might call it a milliard. But that's over in certain areas of Europe. We don't do that. So over here, we use the lowercase m for milli, and that means 1,000th of something, like 1,000th of an amp. But when we look at ohms and we look at kilo ohms and mega ohms, look, we go up to here where it says K. Y'all see K?
Yeah.
What does K mean?
Yes, sir.
Kilo.
Kilo or 1,000 ohms or 1,000 amps or 1,000 volts. So if you see something that says 1 kilovolt or 1 kV, it's 1,000 volts. And then mega is a big M instead of a little m, and it means a million or something like a million ohms or a million whatever. And then you get into like on your cell phones, on your data, you got gigabytes and terabytes. You got gigabytes when you're dealing with memory on hard drives, terabytes on hard drives, gigabytes when you're dealing with your data plans with your phone company. So giga means a billion of something. A billion bytes would be a gigabyte. And then a tera will be a trillion. So download that to your phone, to your computer. I can give you a paper copy if you remind me when you're here, but I do put the I'm uploading all this stuff in there. So, and also other things on the wire chart that we're going to be using on picking wire size, amp ratings and all, and all kind of things. So there's all kind of downloads I put in there for you. And so it's 151 right now technically, and what I can do is the video itself. Do you want to take a minute and see the rest of the video? It's only just another couple of minutes. Does anybody have time to see the rest of it? Or
I'm actually walking to my next class right now.
okay, so we'll pick it up right here next time. Okay.
All right.
Okay.
I can make the video pick up right from where we are the next time instead of letting it play on. Okay.
Okay.
Okay. We'll do that. And listen, y'all go in there over the next few days if you get time, and do the two safety assignments in Moodle if you get time, and then you can be looking at chapter 1 in the book. Chapter 1 in the book, actually,
Right.
you can pretty much read that chapter on your own. I really don't even need to hardly lecture on it, honestly. Except one thing I'm going to throw in. I told Butterball I was going to do this for you, for them. So one quick plug here. Let me share something here. Butterball is starting an apprenticeship program. Butterball turkey plant in Mount Olive and in Rayford. And let me just tell you real quick about this, because I promised their HR lady that I would do this. Now, they've got a program where they will hire you. They'll hire you while you're going to school, and they're paying around $17 an hour starting out if you're an apprentice. They want you to work about 25 hours a week, roughly, up to 25 hours a week. And the requirements are this. You got to have at least 3 of these classes right here already here at the college. PLC programming, that's offered in, the programming end of it's in the summertime. Motor controls is in January. Electrical, you're doing electrical right now, so that will go into one of these. Electronics, that's a part of your motor controls. Among your refrigeration, you're not going to get in. If you had 3,
I'm about to sign off. I'm walking into the building.
Okay, that's fine. Okay, we'll see you Tuesday here in person. You have a nice weekend.
All right.
But if you have 3 of these, if you've had three of these classes here, if you completed 3 of those, then you would be qualified to be an apprentice there. And they are paying good starting out. They're paying 17 starting out for an apprentice. And once you get on full time, then the pay goes up to like $19.35 an hour starting out if you got a degree or a certificate from here. So here's how you apply, and I can give you. I got the flyer up here in the shop at school, but if you want to take a snapshot of that right there real quick, get you a snapshot of this lady here. Let me get still here. If you want to take a picture of that with your camera, Kim Dowdle, she's the program director at Butterball. That's her number, her email, and then you would apply at that website on the bottom right there. But you do have to have three of these classes, three of these in order to qualify to get in as an apprentice. And they're talking, you know, part-time 25 to 27 hours a week. So if you want to get a copy of this, let me know when you're here, or when you come to the shop, you go to our classroom in the shop, just go up to the door and you can take a snapshot of this. And I got both of these sheets. You can take a picture on your phone if you want to, if you're interested in it. You may not be qualified for it now, but you can keep that in mind, because even a year from now, they're going to be hiring. They all the time look at somebody, because they do have some of a turnover rate, you know. But they pay really good, and they got a really good training program. But I'm going to stop the session now, and thank you for joining. Thank you, Benjamin, Roger, and everybody else that was in.
Yeah.
And you're going to, you know, once we get to chapter 2, that's when you're going to be very involved doing calculations on circuits with voltage and amps and resistance, and understanding, getting really into the meat and potatoes of this class is in chapter 2. And from there on out, there's a lot to it. There really is. You'll appreciate it more once we get in there further with it, and you'll begin to understand electricity better, and it's going to help you when you go to diagnose problems and different things, you know, on the job. So,
oh yeah.
Okay. Well, thank you, and again, I'm going to upload the recording when it finishes here. And if you want to go back and watch any of it, or whoever else needs to watch it can go back and watch it. So thanks again, guys, and have a blessed weekend. Thank you for joining. And you can contact me anytime. You can call my cell number, text me during the weekend, got questions, and I'll be glad to talk to you. I don't shut things off on Thursday, as y'all know. So feel free to drop me a text if you want to, or email, whatever. I can hear my emails when they'll ping on here. I can hear it, so I check email all the time. So, but
well, all righty, Durwood. I'm gonna go ahead and get off here.
Have a good one. Thanks for joining.
See ya.
Have a blessed weekend. Bye-bye. Okay. And Benjamin, you have a great afternoon. I'll see you tonight, Benjamin. Yeah. Tell Bill I said hello, and Francisco.
I'll let him know.
Okay, thank you. We'll see you at 6, man. Okay. Bye-bye.